Okay, kiddos, it is hot and humid like hell. I'm sweating like a pig here, but let's wrap up this carbon cycle thing. And we have talked about storage and flow in the water cycle. Similarly, in elemental cycles, you have storages and flows. All the arrows are flows, and the numbers with these items with soil carbon and plant biomass, and the numbers are the amount of carbon in those, and these are gigatons, 10 to the 9 tons, and some of these things here are in concentration. So this is 800 gigatons, so it's approximately 2 times the 400 ppm. This number keeps changing as you keep updating the figures, so this corresponds to some year in the past. So soil carbon storage is 2300 gigatons. If you average all the carbon in all the plants on earth, you will get about 550 gigatons. Fossil fuel carbon has approximately 10,000 gigatons, which means if we take out all of this and burn it without stopping, then we'll put a lot of carbon dioxide into the atmosphere. Ocean is of course a massive storage. There is photosynthesis and respiration and decomposition going on, and ocean sediments, which means everything that is dying and falling to the ground, is getting compressed and forming mud at the bottom of the ocean, and some of that gets compressed like chalk that falls. Corals are made of chalk, calcium carbonate. When that falls, there are a lot of little zooplankton and phytoplankton which are also made of calcium carbonate. When they fall and get compressed, they produce chalks, and there is the Dover Hills in the UK, which is a mountain of chalk, which means when the plates moved around, some ocean floor got brought up and brought up the mountain of chalk with it. So you can see that the surface ocean has 1,000 gigatons of carbon storage, whereas the deep ocean has 37,000 gigatons, largest reservoir of anything here, including the fossil fuel carbon. There are reactive sediments at the top where little microbes live, and they keep mixing it up and consuming organic matter. That has about 6,000 gigatons of carbon in it. And these numbers are not completely accurate to the dot, but they are estimates. So if you look at the flows, you have of course 800 gigatons in the atmosphere, which is a storage as well. Then ocean is photosynthesizing, so it's taking up about 92 gigatons, but respiration happens, and 90 gigatons of that is put back into the atmosphere from the ocean, and some of it is sent to the bottom. And human beings are removing the fossil fuels from underground and burning it and producing 9 gigatons per year. So these are gigatons, these are flows. So this is 9 gigaton per year, this is 92 gigaton per year, 90 gigaton per year. And microbial respiration and decomposition in the soil is producing 60 gigatons per year. Plants are taking up about 123 gigatons through photosynthesis. Some of it goes into the soil, some of it is staying as plant biomass, but plants also respire and release 60. What do you want to understand here? It's that human beings are producing significant amount of carbon per year, okay, but there are sinks, so photosynthesis and soil organic carbon and so on. But note that 123 gigatons may be taken up, but 120 is given back. 92 gigatons may be taken up per year, but 90 is given back, which means a tiny amount like 2 gigatons per year is going down. So we are producing much more than what is being sequestered by the sources into the soil, into the ocean, into the vegetation. And when there is a wildfire and forests burn down, all that CO2 is released as well. which means we have to carefully track all the sinks of carbon that are taking up carbon and not perturb the forests which are taking up carbon, not warm the oceans which take up carbon. If you imagine solubility, if you don't know what that means, which we are too young, don't worry about it, but for those who have learned chemistry, when you put something like salt or sugar or something else into the water and stir it, if it gets dissolved, then you have to understand whether that amount that can be dissolved into the water increases with temperature or decreases with temperature. So we said CO2 mixes dissolves easily into water. This is how we get Coke and so on, carbonated drinks, sparkling water, etc. But we keep it cold. Why? Because cold water holds more CO2. If you let it get warm, it will begin to lose the CO2. Right? Similarly, if ocean begins to warm because of global warming, it cannot take up as much CO2. Plus, there's another important thing to remember that we may come back to later. When CO2 is dissolved into the water or in Coke, it produces something called carbonic acid. It is acid. If you drink too much Coke, it can burn a hole in your stomach. In fact, if you take Coke and put a little coin in it, the coin may begin to melt because it is so much acid in it. So ocean gets acidic when you put CO2 into it, and this is not good for many things that are growing in the ocean. It's called acidification of the water of the ocean. You want the ocean to take up CO2 and put it away to the bottom for a long time, but you also don't want to make the ocean more and more acidic. Okay, so these are the things you have to worry about. This is a descriptive way of doing it. This is from the Woods Hole Institute of Oceanography. Woods Hole is a place in Massachusetts, northeast US, Cape Cod. Woods Hole, they are in Massachusetts, northeast. Okay, so carbon cycle. Carbon moves naturally through ground, ocean and sky in a slow cycle. Over millions of years, people have short-circuited this cycle by quickly transferring hydrocarbons from the ground to air, ion fertilization processes to accelerate the transfer of carbon from air back to ocean. Well, we said something very complicated here. Why does it take millions of years? Because all the plant matter that falls into the soil or into the bottom of the ocean can stay there for millions of years and slowly get converted, metamorphized into coal, oil, gas based on the processes. And we are rapidly digging them up and burning them in a much faster time scales. We are short-circuiting the natural cycle of when they go down and how long they stay and when they come back up with volcanic activity and plate tectonics and so on and so forth. This ion fertilization is a bit more complicated. There are places where you can put iron dust. Remember, your body also needs iron, zinc and so on. You can ask your parents. Somebody may be taking iron supplements or giving you food to make sure you get enough iron. Iron is an essential nutrient. Even for the phytoplankton photosynthesizers in the ocean, iron is a very useful nutrient, which means if you artificially provide some iron to it, it will grow faster, it will photosynthesize faster. So what's happening here? Let's start here. One, plants absorb CO2 from air to grow and decompose to release CO2, or they respire, they burn the carbohydrates they form to grow, to stay alive and so on and so forth. And we have rocks that are eventually being uplifted onto land and weathered to release carbon to soils and the atmosphere. So there is natural geologic processes going on. Weathering, remember, water in the atmosphere dissolves CO2 in the atmosphere, forms carbonic acid, and when it falls onto rocks, it is weathered, which means chemically it is getting dissolved, and that material is flowing into the rivers, into the ocean, and so on as well. But I jumped there. The second step after plants here is iron-rich dust is blown by winds on into the ocean and stimulates phytoplankton blooms. So desert winds from Sahara blow dust, and Middle East winds blow dust. Or dust has some naturally available iron in it. When it falls on the ocean, there is air-sea exchange. Air and water are constantly being mixed at the surface because of the winds and the waves, and that is dissolving some iron and CO2 into the ocean. So phytoplankton, that's the third step. Fourth step, phytoplankton take up CO2 to grow. They photosynthesize and they sink and they come back, and zooplankton eat the phytoplankton and respire CO2. So autotrophs, you may have heard this word. If you don't worry about it. Autotrophs are those that can take sunlight and produce their own energy through photosynthesis, and heterotrophs like us and zooplankton are those that get their energy by eating the autotrophs or the food produced in some way by the autotrophs or by some chemical process. So some carbon sinks to the depths of the ocean in the form of decaying biota. Whales, fish, everybody dies and falls down, and phytoplankton also falls down. And fecal pellets means the animals have their ingestion, digestion and egestion and so on, which all falls. So over millions of years, carbon is incorporated into rocks or turned into hydrocarbons. As I mentioned, chalk mountains of Dover Cliffs in the UK are calcium carbonate deposits in the ocean that have been compressed into chalk, and then the geologic processes have brought them up. So now I should come back to 9. Rocks are eventually uplifted when the plates push into each other onto land and weathered to release carbon to soils and the atmosphere. So this is a nice figure with the processes of the carbon cycle that you can look at and read at your leisure and put it together with these kinds of numbers and the processes that we talked about in terms of how ice albedo feedbacks are changing CO2 in the atmosphere on long time scales. On fast time scales, we are deforesting, we are growing food, and we are building cities, we are burning fossil fuels, we are flying around. Everything we do releases carbon dioxide. The shirt I'm wearing is made by growing cotton or some other synthetic material which needs energy. It's transported, it is processed, and it's made into a shirt, and I buy it, I wear it, and unless I keep wearing it till it's worn down, I'll keep buying more clothes, so I'll be using more energy. So everything we do is energy. All the energy we use now is typically coming from carbon sources like hydrocarbons, so coal, petrol, gas, and so on and so forth. Okay, so I will conclude the carbon cycle with this. There is a lot more material on my website. My channel has a full course on global carbon cycle that you can look at if you want, including some ideas on how CO2 will continue to increase into the future, what that will mean for global warming, what that will mean for everything we do and we want to do. Again, that's your future. You are young if you are listening to this, and the future is yours. So we are basically colonizing your future, so you have to be careful. Okay, so learn and think about these things, because this will affect your future. See you in the next section on some animations of how temperatures change, how precipitation changes, and how the winds change, and so on and so forth. Okay, see you.